But as we go across the column or across the row, Madam Gwendolyn. Yeah. As we go across a row, ma'am, I need you to stop. Oh, you're a sweetie, but go away. So we're going to talk about trends in the periodic table. Um, some of the patterns that Mendeleev saw or that we have noticed since then, sort of as we have done more observations, more research, we see there are more and more patterns that match with the shape of the periodic table. To start off, if we look at the cards that we did in the beginning of this unit, and the circles on the cards, the different sizes represented the radius of the atoms. The colors sort of represented how reactive the elements were, and the number of spokes was represented by the number of, or represented the number of valence electrons. And there were patterns we saw and talked about. And if we go, this is the second period in the table from lithium over to neon. And I do realize I set these two cards in the wrong location. But other than that, pattern of 1, 2, 3, up to 8 valence electrons. And then after 8 valence electrons, it drops to 1 again. And then 1 up through 8. The next element would have 1 valence electron, would go up to 8, the next would drop. So the pattern continues. Also, if you look at the radius, large, and they get smaller and smaller. When we went to the 1 valence electron, it got big again. Smaller and smaller. You would go to 1 valence electron, it would get big again. And the same thing with reactivity. Certain reactivity patterns change as you go across the table. When you go back to the 1 valence electron, you go back to the similar properties from the beginning of the pattern. So Mendeleev saw these patterns and sort of saw that as support for the way he laid out his table. So this shows a graph of radius for the first 3 periods or so. And we have hydrogen, helium is smaller. Lithium gets a lot bigger than helium. And then it gets increasingly smaller. And then sodium gets a lot bigger. Alkali metal is bigger, drops and drops and drops to the noble gas. The alkali metal is bigger. It's going to drop and drop to the noble gas. So that pattern continues following the trends that Mendeleev saw. So if we were to do the circles, similar to the way the circles were on the cards, we had the big circles at the bottom of each family. And if you think about it, that makes sense because you're adding energy levels as you go down. But as you go from left to right, they get smaller, which doesn't necessarily fit with the ideas that we have about atomic structure. So we'll talk more about why we have that pattern that we see. So to talk about why we have those patterns, let's write a few things in our notes. So you have the graph that shows that change that we just saw. If we look at the configuration, and we're just going to do the sort of for the noble gas configuration. So for hydrogen, there's not really any shortening this one, 1s1. Lithium would be its noble gas, and then 2s1, sodium 3s1, potassium 4s1. So the outside is very similar, it's just we get more and more layers. So as we go from hydrogen to lithium, 2 layers, it gets bigger. So going down a column, radius will increase. And that's because of energy levels. Now we want to look at what happens as we go across a period. And so hydrogen to helium, it's still 1 energy level, but now it has more electrons and more protons. lithium all the way over to neon. Neon's going to end in 2s2, 2p6. Argon is going to end in 3s2, 3p6. So as we go across, we still have, say, 2 energy levels, but our electrons change, and more importantly, the protons change. We are going to have a +3 in the middle, and then over at neon, it's a +10. Because remember, we had 1 proton each way across. So +3, +4, 5, 6, 7, 8, 9, and a +10. And what that means is on the 2 rows of electrons, there is a magnet pulling in with the force of 3, or a magnet pulling in with a force of 10. It is a stronger magnet. It will pull those energy levels in closer and make the radius as you go across the table towards the noble gases get smaller. So as we move from left to right, the radius will decrease because of the power of the nucleus. I sometimes compare it to like a classroom with a teacher as the magnet in the middle. So if a teacher talks with a volume of 3, the 2 rows, and it's in a small class, 2 rows of students, power of 3, those students in the 2 rows are sort of leaned back. They're not going to be giving a whole lot of their attention. But if the teacher's talking with the magnet or power of volume of 10, they're being pulled in closer, pulled in and holding their attention. Their class is going to, the circle is going to get smaller. So stronger the magnet, smaller the radius. And then sort of a way that we could show that on a table real quickly, we said that they get larger as you go down and larger as you go to the left. So the largest radius would be found on elements at the bottom left, and the smallest radius will be found on elements towards the top right. So to practice using this trend, let's answer some of these questions. I want you to circle the larger atom in each of the following pairs. So here we are looking for larger. So you want who is going to be closer to the bottom or to the left. So if we have potassium, and potassium is over this way, and cesium, which is like 2 below it, cesium is closer to the big star. It has more energy levels. It will be larger. And then to look at the other pattern going across a period, what if we look at aluminum and argon? Argon is further to the right. It has a stronger nucleus, so argon will be pulled in smaller. So aluminum will be the one that has the larger radius. So if you would take a couple minutes, fill in the answers for number 1, asking for the larger atoms. And number 2 just has you look in the other direction. You're looking for the smaller radius. So here are my answers for these trend questions about radius. And most of them were either in the same family or the same period. But if you get some that are sort of a diagonal kind of question where you have both different periods and different families, you have to sort of think about which one would have a bigger effect. And so an example there would be F, which had us comparing iodine and carbon. So iodine is down here and carbon is over here. So there's not a clear cut, there's, 4 or 5 away. Which one is more important? And the thing that usually will overpower the other for trend questions is the number of energy levels. So 2 layers will definitely be smaller than something with 6 layers. So the 2-layer carbon wins. And a way to show that would be if we use a table like this. So if we are talking about lithium versus sodium, and we want to find out who has the bigger radius, you would first look at the energy levels. Lithium has 2 energy levels, and sodium has 3. From that, can you tell who would be larger? 2 layers versus 3 layers. 3 layers wins, sodium would be the larger. Now, the next question, still wanting bigger radius, wants you to compare lithium, still has 2 energy levels, but this time beryllium also has 2 energy levels. Comparing 2 layers with 2 layers, can you tell who's larger? No. So that's when you need to look at the nuclear charge. Lithium's nucleus has a charge of +3, where beryllium's nucleus has a charge of +4. So the +4, stronger, more powerful nucleus pulls those 2 layers in and makes it smaller. So our bigger radius this time is going to be lithium. Now, the second trend we're going to talk about is ionization energy. And that is, how hard is it to make an ion? And ions are atoms that have gained or lost electrons. So ionization energy is the energy to remove an electron. Sort of like when sodium and chlorine bond together to make salt. Sodium gives its electron over to chlorine so that it can make a bond. Now, the higher the ionization energy, the harder it is to remove the electrons. The lower the ionization energy, the easier it is to remove electrons. And we can relate that to size of the atom, sort of like we related size of a class to size of an atom. So if you are in a large class, you are sitting in the 6th row back. So that's equivalent to you being in the 6th energy level. There's a teacher up front. They're talking, but not super dynamic, so there's not a lot of power to them. You are easily distracted by other things, by your phone or someone walking around out in the middle room, waving at the window or whatever. So you are easily distracted in a large class. It is the same concept. Electrons can easily be pulled away from a large atom. Whereas in a smaller class, you and 3 other people come in for tutoring at lunch, you are not going to be distracted and pulled away by your phone because there's no room for that. Small class, small atom, it's going to be harder to be pulled away. And so we see the ionization graph. It's the same idea that it's a repeating pattern, but this time hydrogen is low, helium is high. Because helium is smaller, it's harder to remove the electron. And then for the second period, lithium, easy to remove, harder and harder as we go across till you get to the noble gases, very hard to remove. Easy to remove from alkali metal, sodium, harder and harder to remove until we get to the noble gases. So that pattern will continue across the table. We were saying that ionization is energy to remove electrons, and we said that it is hard to remove electrons from small atoms. So 1 layer, it's going to take a lot of force to pull away the electron, whereas 2 layers, it will take less force. 3 layers, even less force. And as we go across, we have that stronger nucleus. So this was +11, I think, and this was +3. Stronger nucleus pulls them in further, and that makes it, or pulls them in closer and tighter, makes it harder to remove. So the trend is the opposite of radius. As you go down, it gets easier. And so ionization energy is going to go down as well because it is easier to remove because of the energy levels. More energy levels further away, easier to remove. And as you go across the periodic table, the ionization energy is going to go up, and that's because of the power of the nucleus. So the atom with the smallest ionization energy, easiest to remove, is our biggest atom, and the atom hardest to remove is going to be helium because it is the smallest. So that is our pattern for ionization energy. Whereas the pattern for radius is the opposite. So now you can go through and do the same thing we did for radius. You're going to circle the atoms in each of the following pairs. First, you're looking for higher first ionization energy, so closer to the top right. And then the second one, we're looking for lower ionization. That'll be closer to the bottom left.